Good morning, everyone. This is Dr. Diana here. Welcome to the session on computer organization. In the last session, we have been dealing with the instruction cycle. In the instruction cycle, we have seen that the instruction cycle has four different phases. And some of the phases are common for all types of instructions. The first phase is the instruction fetch. The second one is called as instruction decode. And then you have operand fetch. And the execution. So every instruction cycle has got four phases. The first one is the instruction fetch, followed by decoding of the instruction, and then you move on into the operand fetch or fetching of the data that is required for execution of that instruction. Then you perform the execution of the instruction. And we have seen a primitive circuit that can help us do that. In that circuit, if you can remember, we have looked into the instruction register with 16 bits. Bit 15 is used for the addressing mode bit I. And then bits 12 to 14 are used for instruction code. And bits 11 to 0 indicate the address from which the operand can be fetched. Now, having this in mind, we designed a circuit. This is part of the control unit, and you have a series of gates that form the control unit. From this instruction, this is going to be our input for the control unit. Based on this instruction only, the control unit has to perform something. So, to generate some control signals out of this instruction, we used a 3x8 decoder. We took in these three bits 14, 13 and 12 as input to the decoder, and we generated signals called D0 to D7. And we also used another circuit which is a 4x16 decoder for generating timing signals. The timing signals are from T0 to T15. So you have 16 timing signals and you have got 8 instruction signals. Apart from this, you also have your 0 to 11 bits, which is from the instruction register. This is fed directly into the address register, and you can also have this fed into the flip-flop I. So all of this form the input to our control system. This 4x16 decoder receives its four inputs from a circuit called as the sequence counter or SC. The sequence counter is propelled by the clock signal. So the two inputs that we receive are the instruction register IR and the clock signal. Based on the instruction register and the clock signal, we are going to generate T15 to T0 16 timing signals, and D0 to D7 are 8 control signals. Based on this only, we need to design the control unit. And in the last session, we have seen that the fetch and the decode phase remain the same for all of the types of instructions. There are three types of instructions. The first one is a memory reference instruction. The second one is a register reference instruction. Then you have a input-output instruction. And all these three types of instructions have the same fetch and decode phase. Only after the instruction is decoded, we get to understand what type of instruction it is, and only after that we decide on how to execute that instruction. Until that point of time, it is going to be the same process for all instructions. Now, we have seen what happens in these timing signals for the fetch and the decode phase. In the fetch and the decode phase, we use that timing signal T0, T1 and T2 to complete the fetch and decode phase. Any instruction can take up to T15 time cycles. So no instruction of the basic computer requires more than 16 timing cycles, which is why we have used a 4 cross 16 decoder here to generate 16 different timing signals. So all the 16 different timing signals are generated here. So immediately after you have the T15 timing signal, the circuit will again come back to T0. At T0, you start with the instruction, next instruction execution. That's how the computer works. So this T0 to T15 is going to be repeated until the completion of the program. And the T0, not all instructions require the entire 15 clock cycles. So the sequence counter is responsible for clearing of the timing sequence, which is why it is called as a sequence counter. It counts the sequence of execution of one particular instruction. So once that single instruction is completed, when you complete the execution of one instruction, the sequence counter is going to get cleared, then we are going to start counting from T0 once again. That's the use of the sequence counter. So with this in mind, we are going to see how the operand fetch and the execution phase works in a normal computer. So I have the instruction set, I have the decoders that generate D0 to D7, and I have the decoder that generates T0 to T15, and I have the sequence counter that indicates the completion of execution of a single instruction. So after every instruction finishes its execution phase, the sequence counter has to be cleared so that it can start generating timing signals back from T0. So this is our basic idea. With this idea in head, we are going to use our operations. We are going to design our operations. Yesterday we saw at time cycle T0, what was the operation performed? For instruction fetch, the address of the instruction is available in the program counter. The program counter cannot access the memory directly, so it moves the address into the address register. So at time cycle T0, the content of the program counter is moved into the address register. Now this second time cycle, which is time cycle T1, we have to read the instruction from memory, which is addressed by the address register into the register in IR. IR is the instruction register. It receives the memory content of the address register, of the location pointed by the address register. And once this instruction starts execution, I should increment the program counter to indicate the location of the next instruction. So I am going to increment the program counter value by 1 and store it inside the program counter. It is now inside the program counter. And at time cycle T2, we are going to decode the instruction. How did we mention decoding of the instruction? We are generating signals D0 to D7 from the instruction register. So we need to perform a decode operation of the instruction register, and the bits to be decoded are bits 14 to 12. These are the bits used for decoding, and this is how we form the signals D0 to D7. And what do we do with the rest of the instruction register? Into the I flip-flop, I move the 15th bit of the instruction register. And the address 0 to 11 indicates the location where I can find the particular operand. So that indicates a memory location. So every time we use a memory location or we try to access a memory location, it's always through the address register. I'm going to move that content into the address register. So bits 0 to 11 are moved inside the address register. So this T0, T1 and T2 are going to be common for all types of instructions. And once I have decoded, then I should identify what type of instruction I have to execute, and then I should perform some action for completion of that execution. When I look into that, we have got three different types of instruction. So at T3, I have to identify the type of instruction. How do I identify the type of instruction? There are three types of instruction. The first one is a memory reference instruction. The second one is a register reference instruction. And the third one is a input-output instruction. Now, to differentiate between these three types of instructions, how do we differentiate, or what I can use in the instruction register to differentiate these three types of instructions? Now, we have already seen in the instruction format that for a register reference instruction, the first 4 bits are set to 0, 1, 1, 1, followed by the opcode or the register reference operation. For an input-output instruction, this value is going to be 1 followed by 3 ones and then the opcode. Right? Only for a memory reference instruction, this can either be a 0 or 1, which mentions the addressing mode indicated with the bit I. It can either be 0 or 1, followed by 3 bits which mention the opcode, and then you have the address of the operand. So bits 0 to 11 has the address. Now, when these 3 bits, bits 14 to 12 are 1, it can only be a register reference instruction or a input-output instruction. If its value is anything other than 111, which is the case, 0002, 0, 1, 1, 0. If it is any of these options, then it will be a memory reference instruction. Are we clear till here? So the bits 14 to 12 are used to identify what type of instruction we are dealing with. Now, imagine, how do I identify these from the signals that are here? I have to somewhere identify whether it is a memory reference instruction or a register reference or a input-output instruction. How do I identify? Now, from the instruction register, from the 3 values, from the bits 14 to 12, I've generated 8 different signals called D0 to D7. I'm going to make use of these signals to identify the type of instruction. So we will have a thing like this. Now, the 3 values of the 3 bits which are possible are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These are the possible options for the bits 14 to 12. In that case, we are going to generate signals based on this, and In the case of 000, the value or the signal D naught becomes 1. That's how a decoder works, right? You remember how a decoder works? You get some combination of input and one of the outputs will be activated at any point of time. So only D naught will be 1 when all three zeros are present as the input. When you have all inputs as 0, only then D naught value will become 1. And when D naught value becomes 1, all the rest of the bits are going to be 0, or all the other signals are going to be 0. And when the input is 0, 0, 1, the value D1 is going to be 1. And all other bits D0 is going to be 0, D2 to D7 are going to be 0. So based on this combination, one of the control signals D0 to D7 are going to become 1. The rest of the signals are going to become 0. So we are going to use this method to find out which can be used to identify the type of instruction. Now, D7, if you, 0, 1, 0 gives an output of D2 to be high, 0, 1, 1 makes the output of D3 to be high, 1, 0, 0 gives the output of D4 as high, the rest of the inputs are made, the rest of the signals are made 0, and for the bits 1, 0, 1, D5 is made high, for the bits 1, 1, 0, D6 is made high, and for the bits 1, 1, 1, D7 is made high. So D7 is high only when all three bits are 1. Now, when you look inside the operations or the operation code of the different instructions, we see both the register and the IO operation have the bits 14 to 12 set to 1. So, all three bits are going to be 1 for both register reference instruction and input-output instruction. In that case, which of the signal will be activated for both register reference and input-output instruction? Yes, it is going to be signal D7. Only D7 can differentiate between other types of instruction, a register reference and a IO instruction. So, a register reference instruction or an IO instruction can happen only when the value of D7 is 1. And for any other value, D0 to D6, for any other value, D0 to D6, it will be only a memory reference instruction. Or I can say the complement of D7 dash, or the complement of D7, anything other than D7 will indicate a memory reference instruction. Do you understand the difference? So, the next level after decoding, I am going to immediately look into D7 output of this decoder and find out whether it is a memory reference instruction or a register or an IO operation. Are we clear till here? Yeah. So, at time cycle T3, I have to have two different options. The first option will indicate what happens when I use a memory reference instruction, and the second option is going to indicate what happens when I have a register reference or a input-output instruction. So at time cycle T3, when D7 is complemented, D7 dash T3 indicates a memory reference instruction, and D7 T3 indicates a register reference or IO instruction. Okay. Now I have to identify whether it is exactly a register reference instruction or a IO instruction. How do I do that? I have to look into bit 0. I have to look into the MSB of the instruction register. If the most significant bit 15 is 0, it's a register reference operation. If not, it is going to be a IO operation. So I should look for the bit 15. In the circuit, you can see that the bit 15 is stored in a flip-flop I. So if I value is 0, it is going to be a register reference instruction, and if I value is 1, it is going to be a IO instruction. So I can elaborate this into I dash. I dash indicates the value 0, D7, because D7 has to be 1, and then at time cycle T3, it is a register reference instruction. And when I's value is 1, I have to represent it as I, and D7 value is 1, I D7 T3 indicates an IO operation. Okay, and at time cycle T3, if it is a memory reference instruction, what should I do? I should read from the memory. So when I look into T3, I understand that at time cycle T3, if I have to do a memory reference instruction, then I should identify whether it is a direct memory access or indirect memory access. Where do I see the difference? I see the difference in bit I. If the bit I is 0, it is a direct memory access, and if bit I equal to 1, it is an indirect memory access. So that also I will specify here. So if I is 0, which means I dash, and D7 should be complemented. D7 should be 0. Only then it can be a memory reference instruction. So I have to write it as D7 dash time cycle T3 indicates a direct memory access instruction. And if I value is 1, so I have to mention it as I, and D7 value should be 0, so I have to mention it as D7 dash T3. I have to specify that it is a indirect memory access. So this is at time cycle T3. Based on my decoding, I have identified whether it is a memory instruction or a register reference instruction or it's a IO reference instruction. Now, based on the bits 14 to 12, I have generated the signals D0 to D7, and based on the value of D0, I differentiate between memory access and the other two types of instructions, and based on the value of I have to identify whether it's a register reference or an IO operation or the direct or indirect memory access instruction. So I am going to write a flow chart here which indicates how the program is going to flow. So at time cycle T naught, I have the address register loaded with the content of PC, and at time cycle T1, I have two operations to be performed. One is the instruction register being loaded with the memory content of addressed by the address register, followed by incrementing of the PC value. And at time cycle T2, I have three operations to be performed. The first one is loading of D0 to D7 from decode of the instruction register bits 14 to 12 and flip-flop I loaded with the bit 15 of instruction register and the address register being loaded with the bits 0 to 11 of the instruction register. So this is going to be a time cycle T2 and a time cycle T3. At time cycle T3, I have to check if D7 is 0. If D7 is 0, equal to 0 ante, and check the value of D7. If its value is 0, then it is a memory reference instruction. If its value equal to 1, then it is either a register reference or an IO instruction. To identify what exactly is the type of instruction, I have to now see the value of I. So I am going to check the value of I here. If the value of I is equal to 0, then perform register reference instruction. If its value equal to 1, then perform the IO instruction. If the value of, then to decide on whether it's a direct memory access or indirect memory access, I still have to verify I. So I'm just going to check the value of I. If its value is 0, then it is a direct access. If its value equal to 1, it's going to be an indirect access. So I am going to perform all of this checking at time cycle T3, and at time cycle T3, I have to start executing something. I have decided what to do. Now I should do something. I have not done anything at time cycle T3 yet. I am just looking up some values. At time cycle T3, I can start with the execution of IO instruction or register reference or direct memory access or an indirect memory access instruction. Once the instruction is completed, whatever, how many, I can take T4 to T15. Any number of cycles I can take for completion of that instruction. Once I complete execution of the instruction, I am going to clear the value of SC. I am going to set the value of SC to 0. Setting or clearing of the sequence counter indicates completion of execution of a particular instruction. So I can clear off the SC and then get back to T0. Is that clear? So we are going to use this structure to identify, this is how the instruction cycle works. So in the instruction cycle, at time cycle T0, I load the address of the first instruction from PC into the address register, and at time cycle T1, I bring that instruction from the memory location addressed by the address register into the instruction register and increment the value of PC by 1 to indicate the memory location from which I need to bring the second or the next instruction. Then I see I have got at time cycle T2, I have to decode the instruction, and at time cycle T3 I should start executing of the instruction. At time cycle T3, the next phase in the instruction cycle is actually operand fetch. So I'll be fetching the operand from wherever is mentioned in the time cycle T3. At time cycle T4, I'll start executing the instruction, and at whichever time cycle I complete my instruction execution, that time I'll clear off the sequence counter and get back to the next instruction with time cycle T0. Are we clear till here? And this can be written in our operation language with 4 different values. So I have, it's indicated as I dash to indicate the 15th bit as 0, followed by D7 which indicates 111, and this when done in time cycle T3, it's a register reference instruction, and I D7 T3 indicates an IO operation. I dash D7 dash T3 indicates a direct memory access, and I dash D7 dash T3 will indicate I value should be 1 and D7 should be 0. At time cycle T3 we have the indirect memory access. So these are the types of instructions. Based on this, we are going to look into the instructions set in the next session and find out how specifically for different sets of instruction T4 is going to be handled. With this, I close for today's session. Thank you one and all.